Good afternoon, everyone. I welcome all the participants to the STC, and now we'll resume our afternoon session, which is going to be a lab session. The scheduled session is going to be handled by Professor Monalisa Pattnaik and Mr. Pradimna Kumar Behera. They will throw some light on development of photovoltaic fed LVDC microgrid with hybrid energy storage system. Let me introduce Professor Monalisa Pattnaik. Professor Pattnaik received her MTech and PhD degree from IIT Kharagpur, India in 2006 and 2013 respectively. She is currently an associate professor in the Department of Electrical Engineering, NIT Rourkela. Dr. Pattnaik is a recipient of POSCO Power System Award, Power Grid Corporation of India Limited, India in 2013. Her research areas are power electronics converter control, renewable energy systems, hybrid energy storage systems for EV charging, interlinking converter control in hybrid microgrid applications, and electric vehicle and machine drives. Now, let me speak about Mr. Pradimna Kumar
Thank you,
Behera,
Ananya.
who Mr. Behera received his MTech degree in electrical engineering from Bir Surendra Sai University of Technology, Bulla, Odisha in 2016. He is presently pursuing his PhD degree in electrical engineering at National Institute of Technology, Rourkela, India. His research areas interest include design of power electronic converters, renewable energy systems, hybrid energy storage systems, electric vehicle charging infrastructure, and power management of DC microgrid. Over to you, ma'am.
Yeah, thank you, Ananya. Good afternoon, all. Actually, in this session, basically, this is a lab session, and here in today's afternoon session, we have planned it two halves. In the first session, we'll be introducing me with my student, means basically my research scholar, Mr. Pradimna Kumar Behera. He will be explaining you about how to develop a laboratory prototype. And it's starting from the basic. Here, basically, we are not going to tell the design of the converters and other things in detail, but how to integrate the converters and along with its sensors, and how we have done this power management of a basically LVDC microgrid along with a hybrid energy storage system. Those things from the basics he is going to tell about, mainly about the experimental prototype. Okay. So because from the last from yesterday's session we have learned about, means we have seen many things about the EV system. Morning also we have seen about the power quality and the grid connected systems, and the systems means what we are dealing with. The green energy means the main content of this faculty of this FDP or STC is the power converters for this green energy and EV integration. So where the main component is the power converter, so which we are going to control, we have to measure and we have to do the power management. So that will be discussed in detail from the basics, and here mainly we are focusing on the one prototype, that is the dispatch based control desk. So that will be explained by my student, Mr. Pradimna Kumar Behera. Over to you, Pradimna.
Thank you, madam. Good afternoon to all, and warm welcome to all participants. Today I am going to discuss on the development of
echo is
photovoltaic
happening, Pradimna. Echo is happening, so.
Okay, ma'am. Now
it is fine.
Good afternoon and warm welcome to all the participants. I would like to thank all the coordinators for giving me an opportunity for this tutorial session. The topic of the presentation is development of photovoltaic fed LVDC microgrid with hybrid energy storage system. So these are the outlines of the presentation. I will be briefly discussing about the introduction to microgrids. Along with that, I will be discussing various voltages related to DC microgrid. Then I will be discussing what is the motivation and what are the objectives of doing this research work. Then I will be discussing in detail about the DSpace DS1103 digital controller. Along with that, I will be discussing how we can develop the experimental test bench. Then I will show you the hands-on also for using your DSpace digital controller. After that, we will be discussing the experimental results along with some analysis and discussion will be presented. After that, finally, we can conclude that one. So the learning objectives from this session is the system design and real-time validation of a PV-fed 48-volt LVDC microgrid. Along with that, we will be learning about the operation of DSpace digital controller and the control desk 5.6. After that, we will try to understand the step-by-step procedure for the development and testing of various sensors, signal conditioning units, gate driver units. After that, we will be doing an experimental validation of a power management scheme in the designed autonomous LVDC microgrid. So in the figure 1, we can see a schematic of a microgrid. Basically, a microgrid is an aggregation of local generating units that can be renewable energy sources. It also consists of various energy storage systems and loads, and various power electronic converters are incorporated within it in order to exchange power with the electric grid. This microgrid can operate seamlessly between islanded mode as well as it can operate in a grid connected mode. So there are various advantages that are come aside with the microgrid. That is, it provides a higher efficiency, it provides higher reliability along with the reduced carbon emissions. Along with that, it provides a reduced per unit cost in long run actually. These are the various components of microgrid. As I have mentioned that we can have various types of renewable energy sources like a photovoltaic system and wind energy conversion system. Along with that, for the operation of this renewable energy sources, in order to interface this renewable energy sources, PV panel, wind turbines with the load, we need appropriate power electronic converter. Various power electronic converters are already known to us, like our AC to DC converters, AC converters, DC to DC converters, and our inverters are present. Along with that, various electrochemical energy storage systems are utilized in microgrid that are basically the widely used option is actually battery. Along with that, nowadays, a supercapacitor is integrated along with battery, forming the hybrid energy storage system. The microgrid can power either the standalone load or it can operate in the utility connected mode. Now I'm going to discuss about the various local power generating units that are used within a microgrid. Basically, first one is your solar photovoltaic system, and the inherent power output of a solar photovoltaic system, we know that it is DC in nature and it is non-dispatchable in nature. And various typical power electronic interface that are used are DC to DC converters and DC to AC converters. And for the power flow control of the solar photovoltaic system, basically we are using maximum power tracking system, and we are using the DC bus voltage regulation for the operation of the solar photovoltaic system. The second source, that is our wind energy. The availability is basically based upon the geographical location, and the inherent power output is AC in nature. It is also of non-dispatchable type. In this, we are basically doing the maximum power tracking control. Along with that, if the wind speed is very high, at that time we are introducing a pitch angle control. And along with that, DC bus voltage regulation is done. In case of hydel power stations, it is also the availability is based upon the geographical locations, and the power output in this case is also AC. It is also considered to be non-dispatchable. It is actually this micro hydel is also coming under the renewable category. And the typical interface in this case is the synchronous generator, as well as we can use the induction generators. In this case, the power flow control is done by the AVR that we already know, Actually, that is the automatic voltage regulation and the governor control. And in case of diesel generator, it is actually diesel generator is kept as a backup, and the availability is actually it can be available anytime actually, and the power output in this case is AC in nature, and it is dispatchable in nature. The power output of the diesel generator is in our hand. Whenever we want, we can provide power to the load. And the typical interface in this case is our generator, and the combined heat power plants is basically dependent upon the source, and the typical power output in this case is alternating in nature, and in this case the power flow control is maintained by the governor as well as the automatic voltage regulation schemes. Now I'm going to discuss about the various types of energy storage devices used in a microgrid. You can see the list of various energy storage devices starting from the lead acid, lithium ion, nickel cadmium, vanadium red oxide batteries, and flywheel, capacitor, and supercapacitor. One thing you can observe that the life cycle of supercapacitor is very high, and you can observe that the specific energy of the battery is very high as compared to the as compared to your supercapacitor. However, the specific power of the supercapacitor you can observe here is very high as compared to a as compared to your batteries, whether it is a lead acid battery or a lithium ion battery, it is very high, right? Next, we are basically doing a categorization of various energy storage devices according to different time scales. You can see that for short-term energy storage, we are basically using the flywheel type energy storage devices. We are using the supercapacitors. So what is the importance of using flywheel and supercapacitor as they are basically categorized under the short-term energy storage? You can see that it will provide a sudden fluctuation. If there is a sudden fluctuation in load, then the sudden fluctuation in load can be mitigated over a small time, actually within seconds. And it is basically used in case of welding loads, lift loads, or during a transient condition. And the next categorization is basically your midterm energy storage. And in this case, we are basically considering the lithium batteries, and somewhat we are using the lead acid battery. In this, basically, the load variation is aggregated over a duration of 15 minutes. It is basically used in case of your residential buildings, in which if we encounter some load shedding for around 2 to 3 hours. Basically, it is mostly it is widely used nowadays in context of your renewable energy microgrid. And the next categorization is done considering your long-term energy storage. In this category, we are basically having the flow batteries, and we are having the fuel cell type hydrogen storage, that is your proton exchange membrane fuel cell type. These are basically done to mitigate the seasonal variation in load that is basically aggregated over the day or for an entire year actually. Now I'm going to discuss about the various configurations of microgrid. Broadly, if we classify microgrid, it can be categorized into the alternating current microgrid, direct current microgrid, and hybrid microgrid. In the recent decade, or in the recent times, if you can observe in the last 7 to 8 years, you might have observed that the DC microgrid has become an inevitable part of the modern power distribution system with higher efficiency and reliability. So what is basically a DC microgrid? It is also a controllable system consisting of group of distributed energy resources. We can have renewable energy resources. Along with that, we can have energy storage system, or we can have the hybrid energy storage system that are basically connected through a common DC bus, and they can supply the local loads or the standalone loads present. There are various potential bus voltage levels of DC microgrid. They are basically, I have categorized them into four categories. Voltage, first bus voltage is less than 48 volt. The use of this voltage is used for the automobiles, USB lightning, or powering a small house and some standalone facilities. The main feature of this is it is highly safe, and the loss associated is actually more. But the requirement of any protection as the voltage level is low is not required. Next categorization is in between 48 volt and 100 volt. It is basically used in your low power appliances for lighting, residential, telecommunication industries, and various standalone facilities. It is still safe, but in this we incur more losses. In this also we do not need any extra protection, and it can power loads of few kilowatts actually. And the next categorization is, or the voltage level is in between 100 and 400 volt. It is basically used in your data centers. But in specifically, if I say in case of your data centers, where you basically using 380 volt. This is used in your residential and major appliances and industries. In this, loss associated in this system is very less. But however, the protection in this case is very important because DC above 120 volt is actually considered as lethal. So this is basically suitable for powering loads or industrial loads up to 500 kilowatt. And the next range of voltage is in between 400 to 1500 volt. This is basically used in case of your shipboard power system, aircraft power system, transportation facilities, transportation systems, especially your traction system. And in this, the power range is actually around in megawatts. Actually, it is up. It is more than actually 10 megawatt. In this, the compulsory protection is important. So now, as I have discussed, various potential levels of DC microgrid, but the problem is that the lack of various standards, actually proper standards and codes, along with that misconceptions regarding the safety and efficiency, actually has hindered the widespread usage of DC microgrids. So basically, it can provide an opportunity to us to create a global DC standard. The basic motivation for going for a DC power system is that the various renewable energy sources like your PV system is intrinsically DC in nature. Along with that, we do have a superior compatibility of DC energy storage techniques such as your battery and supercapacitor. Nowadays, large number of appliances in our household, offices basically run on low voltage DC, starting from your mobile to your laptop, or nowadays also BLDC fans are there. And wind energy is also considered, can be considered as an attractive solution in case of DC microgrid, as it is complementary with respect to our solar photovoltaic system. So these are various motivations which provides us an opportunity to create an ecosystem or a DC microgrid system with increased efficiency, reliability, and your energy independence. So the development of one standard, that is your IEEE standard 2030.10. It is basically a standard for your rural and remote electricity applications. It is considering 48 volt DC bus voltage level as the most economical from the cost and the performance point of view. So with this motivation, the primary focus of this work is basically related to the design, development of a LVDC microgrid, considering photovoltaic as the major renewable energy source, and it will be integrated with the hybrid energy storage system. This is basically the architecture of the LVDC microgrid. You can see here, you can see that solar and hybrid energy storage system that is comprising your battery and supercapacitor considered as the primary distributed energy resource. And you can observe that these distributed energy resources are connected to the common DC bus. The photovoltaic system, the battery, and the supercapacitor all are connected to a common DC bus. We can see that a lead acid battery and a supercapacitor pack forming the hybrid energy storage system are connected to the DC bus via dedicated DC to DC converter. Battery system is having a dedicated DC to DC converter, and the supercapacitor is also having a dedicated DC to DC converter in this case. The hybrid energy system basically provides, or we can say that it smoothens the power fluctuation that is arising due to the erratic nature of your photovoltaic system, as well as it maintains the constant DC bus voltage. That is, in this case, it is considered to be 48 volt, regardless of the demand and generation disparity. And due to the limitations in terms of your specific power, the battery fulfills only the average power demand, while the supercapacitor is kept to fulfill the short-term transient that will be coming during the load variation or wind speed variation or irradiation variation. These are certain kinds of variation that arises in a system actually. And the power management, you can observe that it is categorized into the two levels. One is the low level control and other one is the high level control. The low level control is basically allocated for the DC bus voltage regulation and power sharing among the battery and supercapacitor. However, the high level control is basically allocated for SOC management and power allocation. Along with that, it can also perform some sophisticated functions like your weather monitoring. These things can be done in your high level control. Now I'm going to discuss about the design and development of the solar photovoltaic generating unit. You can see in figure 4, the configuration of the PV system is shown. That basically comprises of your PV module, a buck converter, load is there, and MPPT controller is present. The operating point of a PV panel is basically determined by the impedance matching of the PV panel with respect to the load. However, if we connect a load directly with the PV panel, that may not give a value or a power value which will correspond to the maximum value of the PV panel. So in order to overcome this challenge, actually we are integrating a DC to DC converter. In this case, we are using a buck converter. Right? The duty ratio of this converter is controlled to ensure that PV panel operates at maximum power corresponding to its maximum current and voltage irrespective of the irradiation and load change. And in ideal conditions and absence of any parasitic elements, the relationship between the input variable and the output variable, the input variable in this case is your VPV and the output variable in this case is your VDC. And the steady state relationship is given in 1, and the efficiency, if we calculate, it will be represented by your equation number 1. The relationship for efficiency is given in equation number 2. In figure 5, you can observe the different IV and PV characteristics corresponding to different value of irradiations. Next, the load impedance reflected to the input side of the buck converter is given by equation number 3. So according to the aforementioned calculation, a buck converter will track the maximum power whenever the load resistance is less than or equal to the internal resistance of the PV panel. So how we will determine the internal resistance of the PV panel? Simply, we have to divide the voltage during the maximum point by the maximum current. VMP by MP will basically provide us the characteristic impedance or the internal resistance of the PV panel. Now I will be discussing about the design of the buck converter. By varying the duty ratio of the buck converter, we can align the operating point in such a manner that it coincides with the maximum power point of the PV panel. So if we consider the continuous conduction mode of the converter, then the filter value, the filter inductor of the buck converter can be determined by using your equation number 5. That is your VPV into 1 minus D by the switching frequency into the ripple value of current or the ripple inductor current. In this case, we have considered 10% of the maximum value. And in order to design the DC link capacitor or the DC bus capacitor, the formula given in equation number 6 can be considered. And in this case, the ripple voltage is considered as 1% of the rated value. It is considered 1% of our 48 volt, that is your 0.48 volts. Now I will be discussing about the development of bidirectional converter for hybrid energy storage system. So among various energy storage technologies, till now we are using the most widely used electrochemical energy storage devices. And the energy storage technology basically includes our batteries and supercapacitors. And basically, power electronic converters are required in order to ensure the interface between the DC grid and the energy storage system. And these converters basically operate bidirectionally. Major types of power converters that are used in case of your hybrid energy storage system or energy storage system is your AC to DC converter. And the DC to DC converters are basically classified into our non-isolated type, and other categorization is the isolated one. The use of hybrid energy storage system is basically to maintain the power disparity between the renewable energy sources and the loads. And first of all, what we are doing, we are basically segregating the current component, the current required at the DC bus into two components. One is your low frequency component and other is the high frequency component. And what we are doing, we are basically employing the low frequency fluctuations to the battery, while supercapacitor is basically utilized to provide the high frequency fluctuations that arises due to various transients in the system, as it provides very fast response. Basically, the determination of the appropriate frequency, that is their FTH, is very crucial, and it depends upon the response time of the battery and supercapacitor that are connected in the system. Since we know that the response time of battery varies from milliseconds to seconds, different literature adopts different value of this threshold frequency. For instance, we can say if in literature, some have set the threshold value to 5 Hz and some are using threshold value to 0.2 Hz. So from here, we can conclude that in an integrated system in which wind energy system or PV system are present, along with that hybrid energy storage systems are present. So the threshold frequency of the hybrid energy storage system will actually vary. So how we will determine this threshold frequency? In order to determine the threshold frequency, we can use the Regan plot, or in laboratory, what we can do using the battery and supercapacitor, we can perform some iterative experiments for step changes in load, for step change in wind profile if it is a wind energy conversion system, and for step change in irradiation also we can check. And by this we can plot the response and determine the threshold frequency. We can plot the response of the supercapacitor current and battery current, and we can analyze that one, and we can determine the threshold frequency for the hybrid energy storage system. So the prime objective of the energy management in a hybrid energy storage system basically provides a dynamic load power sharing. The main aim here is to efficiently allocate the fluctuating load power among different energy storage devices connected. If we have multiple energy storage devices, so the energy management system or the power management system should be capable enough to segregate the total current requirement of the load and appropriately allocate to battery, supercapacitor, or if fuel cell is present. So the threshold frequency should be allocated in a proper manner. The next objective that is basically fulfilled by our hybrid energy storage system is the DC bus voltage regulation. So the control should be quick enough to restore the DC bus voltage if it is subjected to various transients. Along with that, the SOC regulation of the battery and supercapacitor within their optimal range should be maintained. The optimal range is considered for battery, it is considered to be within 40 to 80%. And in case of supercapacitor, the normal operating range of the SOC of the supercapacitor is in between 25% to 90%. It is very crucial actually. We need to monitor the SOC of the supercapacitor and battery to maximize the operational lifespan and ensure that they are effectively utilized. The last and the prime objective of for doing energy management is basically nowadays we know that EV application is in a boom actually. So it should be the hybrid energy storage system should be capable enough to capture and store the power during regenerative operations in case of your EV applications. Here the circuit diagram of the non-isolated DC to DC converter is shown. You can see that it basically uses a small number of passive elements and a smaller inductor. And as compared to the chuck converter and SEPIC converter, it offers a lower current strength for the active switch, whether it is MOSFET or IGBT, and the diodes, and it offers a high efficiency. And during, if I talk about the operation of this non-isolated DC to DC converter, during the step down mode or the buck mode, and the battery is in charging mode. In this case, the upper switch will be on and the power flow will be from the DC bus voltage side to the battery side. And the power flow is reversed in case if it is operating in the step up or the boost mode, that is the discharging mode. And in this case, the lower switch will conduct and then the power will flow from battery to the DC side in this manner. Now I will discuss about the filter design of the bidirectional converter. There is just now I have mentioned that the operation of the converter during your buck and boost mode. So the filter components of this bidirectional converter during the boost mode can be determined using your equation number 7. And the operation and the filter value during the buck mode of operation can be determined using your equation number 8. Since the converter either operates in boost mode or buck mode, so we need to select an inductor in such a manner so that it should satisfy the current ripple criteria during both the modes. So for this case, what we are doing, basically we are selecting the maximum value that will be coming, and that value we will be selecting so that we can fulfill the criteria of current ripple. And similarly, in case of a supercapacitor, the inductor value can be calculated. And the DC link capacitor, based on the voltage ripple specification that we have considered in this case, is 1% of the rated DC voltage, can be calculated using your equation number 10. Now I'm going to discuss regarding the real-time implementation using your DSpace DS1103 digital controller. Here I have shown the various DSpace components and accessories that come along with the package. We have the DSpace DS1103 R&D controller board. We have the DSpace box. Along with that, a license key is provided. And we have the LED and connector panels. That is basically we can say this one as the breakout board. So basically the major RTI library of the DSpace is categorized into two parts. One is their master PPC and other one is their slave DSP. Both are basically used to generate the control signal and interface the feedback signal. And we have a control desk. That control desk is basically a software tool which is interfaced with the MATLAB and the RTI library. And the signals from the sensors are fed to the controller through this breakout board. And both the control of signal and outgoing signal and the feedback signal are controlled and monitored in the control desk. This is your real-time interface library. If you double click any of these blocks, means you can find the necessary blocks that is required while building your simulation. And then along with that, we have some demos that are present. And along with that, we have a help menu that is basically useful. If you're facing any difficulty, you can double click the help menu, and lot of informations are present that might help if you're facing any difficulty while doing or making the simulation. So this is basically the breakout board. In this, I have categorized them into 8 parts. You can see the number 1 is related to the ADC channel. Here we have the 20 number of ADC channels are present in our DSpace DS1103. And in this, we have 16 number of multiplex channels. Channel 1 to 4 are multiplexed with each other. Similarly, channel 5 to 8 are multiplexed with each other. Like this, we have multiplex channel up to channel number 16, while the channel number 17, channel number 18, and channel number 19 and channel number 20 are the parallel analog to digital converters. And the section 2 basically represents the digital to analog converter. Basically, from this channel, we can provide the PWM signal to the converter. However, the frequency range for this digital to analog converter channels is will saturate basically at 5 kilohertz. You cannot go beyond 5 kilohertz from this channel number, means from this digital to analog converters. The next one is your third one is the slave ADC channel. The fourth one is the digital input output interface channels. Fifth one is the slave IO channels. And the sixth one is your incremental encoder channels. Basically, if you want to sense the speed and feed it through these channels only, you can do that. And the 7 is the CAN connector, and the 8th one is the RS232 and RS432 serial bus. Now, this is basically as I have told you that DSpace digital controller is categorized into the slave part and the master part. This is basically the master PPC. By clicking in any of these blocks, you can access the IO functionality associated with the respective processors. Basically, in case of your in this DSpace digital controller, there are two processors are present. One is handling the master PPC and the other one is handling the your slave F240. This is the breakout connection of the digital IO connector. This one is the interface of the slave DSP board. In this, we can get the various PWM channels. We can perform the sinusoidal pulse width modulation. Various types of multiple pulse width modulation, state vector modulations can be done. And the breakout of the slave IO connector is shown here. Here you can observe that channel 1 is ground, channel 20 is ground, channel 37 is ground. All these are basically your common ground. Any of the, if you want to take a ground connection, right? Suppose I want to get a PWM signal from, we can use the channel number 7, but it will come with respect to a ground. So I can use pin number 1 or I can use pin number 37. All these are common ground. Now I'm going to discuss about the design steps that are involved in while doing the simulation in MATLAB and control desk. First of all, I will discuss about the MATLAB model. So these are some of the steps that need to be followed while configuring the parameters and interfacing with the control desk. First of all, you have to launch your MATLAB. Right? DSpace DS1103 basically supports version lesser than actually 2016A. And then you have to create a Simulink model. You have to design and save the model, and you have to set the stop time to infinity. And then you have to press Control E, and you have to open the configuration parameters, right? Then you have to set the solver into Euler 1, and you have to uncheck various, if optimizations are checked, that you have to optimize, and you have to select a fixed step size. And similarly, you have to set up the hardware configurations. So the device vendor and should be generic one, and the device type should be custom, and the integer should be int, and floating and signed integer divisions should be rounded to 0 actually. Then after doing all this till your step number 7, you have to click apply and OK. Now you are ready to build your model. So in step number 9, you have to build the model, and you have to actually verify the diagnostic viewer, and you have to check whether any errors are coming or not. If errors are there, then you have to rectify the error. Otherwise, it will show that the build process is 100% successful. Then after the build process is successful, an SDF file will be generated that will be loaded to the DSpace control desk actually. Next, I am going to tell about the control desk operation. So you have to check the pulse results in the slave IO connector. Then you have to check the various MATLAB simulation blocks can be found in the variable descriptions, and you have to select the SDF file, and you have to, in the model root you have to drag various measurements means that you want to see in the control desk, and then you have to import the SDF file. After completion, you can go to the step number 11, right? And you can press the go online button. So if you press the go online button, then you can say that your plant is in interface. Plant is in interface with your controller. So these are the things I will be actually showing a demo after this presentation is over. As I've told about the analog to digital converters, now I'm going to discuss about the how we can do the signal scaling actually. Previously, I have told that we have got 16 number of channels, right? Those are actually multiplexed one, and for them the resolution is actually 16-bit, and the input voltage range is 10 volt. And we have 4 parallel analog to digital converters, and the resolution for this converter is 12-bit resolution, and it is having the same input voltage range of 10 volt. And it is very important to understand that whenever we are doing the scaling, if we are acquiring a feedback signal through a signal from the plant, and we are feeding to the analog to digital converter, so the physical input signal must be within the range of -10 and +10 volt. So whenever this is maintained, DSpace will scale this by a factor of 0.1. So if I have a value of 10 volts, then it will be scaled to a value of 1 volt. So we need to take the ADC signal and multiply by 10 in order to remove the scaling factor actually. And now I will discuss about the digital to analog converter. As I've already told, we have the 8 number of DAC channels. These channels are basically having the 16-bit resolution, and the voltage range in this case is also same. It is within 10 to -10 to +10 volt. And this block also offers two operation. It can operate in either it can operate in transparent mode. That is, the channel output will be immediately will be converted and provided to you. And the second one is the latch mode. That channel is converted and it will trigger only after, if we give a synchronous triggering in the control desk, is if it is present, then only after that it will trigger. So now I will discuss how we will be building the Simulink model. Once we have actually defined the model, right, we have to do some parameters changes in the simulation. To do this, what we have to do, we have to go into the configuration parameter window, right, or directly we can use the shortcut Control E, right. There we have to set the stop time to infinity. You have to keep the solver to the ODs E1, that is the Euler type. You have to provide a step size for your experiment. Next, what you have to do, you have to uncheck various things. That block reduction optimization should be unchecked, and conditional input branch execution should be in the checked condition. So, first from the PC operating system, you have to enter into the control desk environment. You can see a shortcut like this, right? And you have to launch the control desk. If this shortcut is not existing, then from all the programs where it is loaded, you can easily find this icon, and you have to double click this one, and an illustration that is displayed over here will pop up actually. So it is basically segregated into 6 zones actually. First one is your project zone. To the extreme left, you can see I'm marking it with the red box. Actually, this is the project manager zone actually. The second zone is related to the measurement configuration zone. The third one is related to the properties, various properties related to various measuring instrument that will be using, display, time plotter, gauge or sliders that will be using. Those properties will actually be visualized in the property section. And the fourth section is basically the variable browser. After you have loaded the SDF file that we have generated after building the model, here all various types of variables will come under the model root section. And the fifth one is related to your measurement data pool, right? And the sixth one is the platform device manager. From here, if you press this one, you can see that whether your controller is online or offline. You can check this one. Also, this control desk provides various other functionalities. So if you press the view menu and go into the control bar, you can find various functionality like user function input, and you can see the various instrument selector, platform device, layout navigator can also be seen from the view menu actually. Now suppose we want to prepare the tutorial project. So from the file menu of the control desk, we have to select the new project and project with along with the experiment. So then control desk will basically open a dialog box that will show you define a project. Now you have to enter the name of the project, any name you can give. You have to enter the name of the project, and it will be stored in some root directory actually within your PC. Next, then if you press the next button, then you have to define the name of the experiment. So you can give any name. Here I have mentioned actually MPPT single PV I have mentioned. So then you have to press the next button. After you press the next button, control desk will open the add platform device dialog. Here, whichever board is connected to your system should be selected. For my case, as I have connected DS1103, so I will be selecting the DS1103. If you have DS1104 board or Autobox, or you have the Scalexio board, then you have to select this and you have to press the next button. Then you have to import the SDF file and for your real-time hardware from operation from there actually. Then you have to press the finish button. Now, if you press the finish button in the project manager, you can see the various project structure that you have created so far will come in a linear fashion. Actually, you can see all these have come actually. Here, all the things will be present for your easy visualization actually. Now, we will try to understand how we can measure variables that are actually feedback from your plant into the controller. So in order to measure the variable values of a running real-time application, we have to connect different instruments to the variables. So various instruments that are available in the control desk are your plotter. We do have a display. We have a gauge menu. We have a knob. We have a slider. We have a variable arrow. After that, in order to display or change the property of the instrument, you can click on the, suppose I have selected a plotter, then I can click on the plotter. Then if I select the property, then I can change the size and position, the width and height of this plotter. I can also select where I will place my cursors. It is basically having the X cursor as well as the Y cursors that can be selected from here. Next, how we will expand the time frame. This is basically a typical task that is usually faced by various students actually. In order to expand the time frame, what you can do is basically you can use the trigger menu that is basically present. You can use the trigger menu, and if you set the duration to 10 seconds, so this this plotter menu will be expanded and the zoom version can be seen. Also, you can change the minimum and maximum values of the y-axis in the property tabs of the plotter, and you can change the scaling mode from fixed to variable type. Now, if you want to capture the measurement in your computer hard disk or any storage device, so you have to, first of all, you have to click the measurement menu. Then you have to view the measurement configuration, or directly you can, if you want to use a shortcut, you can press Ctrl M. So on the measurement configuration tab, you can see recorders will be present. recorders will be present. Then what you have to do is you have to right click on the recorder, and then you have to create a new recorder. Then this property will come. This is shown in the right side of the screen actually. So you have to name, you can name any name you can give to the recorder, right? Then you have to press the automatic export button, you have to press. Then you have to give the file name and how you want to export that. Whether you want to export it into .NET file or .idf file or various types of files are there. So for our case, we are basically using the .NET file. Prior to, again, if you want, suppose you have stopped the experiment, right? Again, you want to rebuild the model, and then you have to press the Control F8 button, and you have to go into the projects that will be listed, and then you have to go to the hardware configuration and right click, and again you have to select another SDF file, and you have to reload the variable description. This is the experimental test bench of the developed system in our laboratory, and the parameters of the LVDC microgrids are shown over here. So this one is consisting of the for PV system. I'm using a PV emulator, and we have a two numbers of battery stacks are present rated at 24 volt. We have two numbers of supercapacitors rated at 32 volt. And these are some of the production units. We have the sensor boards. We have the bidirectional converter 1 that is used for your battery, and the bidirectional converter 2 that is used for your supercapacitor. This is the buck converter that is used to interface the PV panel with the load. Here we are using the resistive load, and here you can. Yes, I am using the. Here is the D-space breakout board. This one is the D-space breakout board, and basically we are using, in order to sense the voltage, we are using the LEM make LV25 sensor. And for sensing the current, we are using the LEM make 55P rated at 50 ampere. And the sampling time we are considering as 20 microsecond. And the switching frequency of all these converters are at 10 kilohertz. Now I will show you the demonstration of the system actually. So first of all, you have to open the MATLAB. If you already, my MATLAB is open. Once again, I'm opening this one. So if you open the MATLAB, so it will, one pop-up will come that which platform you want to select. If you are having the RTI 1104 DSpace DS1103 controller, then you have to select RTI 1103. Then automatically it will show that the RTI library along with the RTI FPGA are all these are registered, and RTI platform support for this controller is activated. This thing will, first of all, it will pop up. So next thing what you have to do is you have to build your simulation model, right? So for building the simulation model, you can use your Simulink library, or you simply you can write RTI 1103. So the RTI library will pop up, and in this we have various types. Here you can see that master PPC and the slave PPC boards is there, and we have different types of block sets will be present. Those can be used actually. And if you select the master PPC, from here we can take our ADC channel, and this is our DS1103 ADC _C17 is basically our parallel analog to digital converter. And this MUX ADC are our rest 16 number of channels. We do have encoder setup. Along with that, various types of bit in and bit out blocks are there. If I go back, if I enter into the slave DSP channel, slave DSP zone, here various types of PWM processing units are given. This is basically the DSP PWM. It is used for PWM for DC to DC converter. This one is the DSP PWM3. This PWM3 will be used for sinusoidal pulse width modulation in case of your AC systems. Along with that, we do have the space vector modulation. This is the space vector modulation block. All these things can be used for performing your real-time experiments. So already I have modeled the simulation model. And so you have to press Control E. If you press Control E, configuration parameters window will pop up actually. Then what you have to do, you have to go to all parameters. You can search if you're not finding any parameter, you can directly search that one. See, you can see that I have kept the stop time to infinite, and I have selected the fixed step size. And for my system, I'm using the OD4 actually. Rangikuta solver I'm using. Along with that, you have to uncheck the signal storage reuse. You can directly search the signal storage reuse. You can see that signal storage reuse is unchecked over here. One more thing you can search is you have to uncheck the block reduction optimization. Block reduction optimization, if you search the block reduction optimization, you can see that the block reduction optimization is also unchecked. So these are the certain things that should be maintained while you are using the DSpace digital controller. So after you have built the simulation model, then what you have to do is you have to press this button, that is the building button actually, or you can directly from the keyboard you can press Control B, and you can see the diagnostics. Once again, I will build the model. See, if you press this button or directly press Control B, your simulation model is built, and it will be converted into a .hdf file actually. And this .hdf file will be located in the root directory where you have kept your simulation model. For me, I have kept the root directory as your in this folder actually, PCGEEI. I have kept the folder. I have kept my simulation model. Here only the SDF file will be generated. You can see here it is showing that it is building our model. In the extreme bottom of the screen, you can see it is building the model. Now it is showing that it is ready. If I press this one, you can see that successful completion of Simulink coder build procedure for the model PCGEEI tutorial is completed, and it is successfully built. Means it is 100% successful for this one. So next, what you have to do is you have to open your control desk. So if you open your control desk, I will close this one. Again, I will open this one. So in the all program, you can see the icon over here, DSpace Control Desk 5.6. If you click this one, it is showing around 66% it is completed, and it is initializing the user interface. Now it is trying to complete the setup. Now it is showing that platform is finished. Now you have to select a new project and you have to provide a name of the project. Let's say we will give it a name, project underscore PCGEEI-1, and you have to select the root directory. After selecting the root directory, you have to press the next button. Then you have to give the name of the experiment. Let us keep it as PCGEEI tutorial 1. Then you have to press the next button. Now it will show various platform and devices that are actually present. So for this we have the DS1103 PPC controller board. You have to select this one and you have to press the next button. Now here you have to import the SDF file. The SDF file will be kept in the root directory where you have kept your simulation model. So for me, the root directory is basically here within this one. This is my SDF file. This one I have to select. If you double click this one, this will be automatically selected. And then you have to press the finish button. If you press the finish button, one more window with dotted grids will come. Then suppose I want to measure the DC bus voltage of the plant, or I want to measure the battery reference current, actual battery current. So these will be located in the variable sections. In the variable sections, if you click this one, the project PCGEEI tutorial.sdf, you can find the model route. If you find the model route within the battery to supercapacitor controller, you can find that we have suppose I want to measure the battery reference current. I want to visualize the battery reference current. I will drag it into the dotted grid, and you can find that various types of options will pop up actually. So you can use the display. So if you use a display and if you drag it, it will actually become big. Now suppose I want to see the battery reference. Similarly, you can drag it, use this one, and you can visualize the battery reference value. Along with that, if you want to plot it, you can use the time plotter menu. Simply, suppose I want to plot the time plotter of the battery reference current or actual battery current. What you can do is you can bring and you can select the time plotter. If you see the time plotter, here you can, if you go into the layout navigator, if you go to the instrument navigator, you can see that one signal is appearing, that is your battery reference current. In this way, for every variable, whatever variables are there you want to measure, you have to do in this manner. So already I have done that. So I will close this one and I will open the model which I have already kept for this demo. Here you can see that I have taken the load power, battery power, power of the supercapacitor, SOC of the supercapacitor along with SOC of the battery. PV power is there, voltage of the PV panel, current of the PV panel, supercapacitor current, supercapacitor reference, battery actual current and battery reference current. Along with that, the DC bus voltage. So what I have to do is, suppose I will rebuild the model once again. Now it is building the model. The platform is connected and it is showing that build process is completed successfully. After this build process is successfully completed, you have to press go online button or directly also you can press the start measuring button. So if I press the start measuring button, so it is showing that that application has detected a variable change to the original imported description. So you have to press yes. Again, it will show some that the variable description will be reloaded. So if you want to reload the variable description, you have to press yes. Otherwise, if you don't want, then you can press no. So for me, I want to reload the variable description. Now you can see that the battery voltage is around 23 volts and the supercapacitor voltage is around 25 volts, and our system is now in online condition. But we have not applied any PV voltage, or we have not applied any, not turned on our battery and supercapacitor system. So this is very important. So the controller should be in online condition while you are performing the experiment. Now, what I'm doing is I will be turning on the PV system. Already my rotate this part. This is our PV emulator. This is our PV emulator. This is another computer interface for this, specifically for this your PV emulator, right? This one is our load box. Once again, I will repeat. This is our load emulator, and this is a dedicated PC for operation of this load emulator. It is basically having a software that is being interfaced. That is, this is a iTech make, and it is a SAS software for this specifically for this PV emulator. This is our host PC. This is our host PC that is basically controlling the this DSpace controller that is interfaced. It is basically acting as a interface in between our plant and the controller. This is our load box. This is our load box. These are the two battery packs. These are the two supercapacitor packs that are rated at 32 volt. This is the protection unit for this supercapacitor unit. I should go actually. Okay, now I will turn on the PV output. So here you can observe that in the screen, you can observe that the output power of the PV panel is around 165 volt. This is basically during irradiation of 500 watt per meter square, and the PV system is operating at maximum power. Now I'm changing my load. If I change the load to 15 ohm, suppose my load resistance to 15 ohm, then you can see that it is the MPPT is able to track the corresponding maximum power at 500 watt per meter square. Once again, I will introduce a load change. Just now I have introduced a load change. You can observe that the perturbation in duty cycle is going on, and the MPPT controller is trying to make the, or it is actually trying to extract the maximum power. Now you can see that the power have again reached to 165 watts at an irradiation of 500 watt per meter square. Here you can observe the SOC of the battery is showcased, and here you can see the SOC of the supercapacitor, but the actual current of the battery here is zero, as I have not turned on the battery and the supercapacitor. The actual current of the supercapacitor is also zero. And the output DC link voltage, the DC link voltage during this condition is maintained at 44 volt actually. But for our system, we want to maintain the DC bus voltage at our rated value, that is the 48 volt. So for that, now what I will be doing, I will be turning on the battery and supercapacitor. I will be interfacing the battery and supercapacitor system. Now you can observe that the power required by the load is around 190 watt, and the power supplied by the PV panel is 165 watt, and the rest required power of around 28 watt is given by the battery. You can see that the DC link voltage is maintained stiff at 48 volt. Now, let's say I will introduce an irradiation change. Now I am changing the irradiation to 600 watt per meter square. If I introduce, till now I have not introduced, just now I will be introducing the irradiation value of 600 watt per meter square. If I introduce the, so what will happen is, you can see that the power output of the PV panel is around 200 watts. This is the maximum power corresponding to your 600 watt per meter square, and the load requirement is 190 watts, and the battery is actually absorbing the excess power of around 5 watt. You can observe that one. And now suppose, let's say I will introduce, once again I will introduce a change in your irradiation. Let's say I will make it to 750 watt per meter square. Now I have introduced irradiation of 750 watt per meter square. You can see that the power provided by the PV panel is around 245 watt, and the excess power that is present, the load is consuming the same 190 watt, and the excess power is absorbed by the battery. You can see that the battery current is negative. The battery is absorbing a current of 2.4 amperes, around 2.4 amperes. Now let's say I am decreasing, once again I will decrease the irradiation to 500 watt per meter square. You can see that the controller is swiftly maintaining the DC bus voltage, and it is working properly, and now the power deficit power required by the load is provided by the battery. And you can observe that the battery current is now positive, while the DC bus voltage is maintained constant. So this is we are doing this, whatever experiment we have done, this is for the irradiation change. Now I am going to introduce a load change. Let's say I am introducing a load change. Now I have made the load resistance to suppose 15 ohm. So the load power is going to decrease. Here you can see that the load power has come down to 150 watt, and the power generated by the PV system is around 165 watt, and the excess power is absorbed by the battery. Once again, I will introduce another load change. Suppose I will now change the load resistance to 10 ohm. If I change my load resistance to 10 ohm, the power required by the load is around 225 watt, and the power that is required by the excess power, that is the deficit power that is required by the load is provided by the battery. However, In all these transient scenarios, that is your irradiation change and your load change condition, the DC bus voltage is maintained constant at 48 volt, irrespective of these changes. So this is all about the experiment part. Next one is, suppose we want to do the recording of this one, and suppose we want to plot how the results are actually coming. So what you have to do, you have to go into the measurement configuration. Here one pop-up will come. There you have to select recorder one. You have to right click. You have to right click that one. Then you have to, I have given the name as recorder one only. Then you have to go to the storage information. You have to check the automatic export. You have to give a name. Let's say I have given exp1 underscore, and how you want to export this one. Various types of files are there. I want my stored data in .mat file. So I will select .mat file, and automatically automatic export name will come, and that is shown over here, exp1 underscore 004 .mat file. So now the system is running. You can see that the power required by the load is 225 watt. The power provided by the PV panel is around 166 watt, and the power supplied by the battery is around 70 watt. So what you have to do, you have to, if you want to record the data, you have to press the start immediate button. See, if I press the start immediate button, so what is happening here? You can observe that the recording is going on. Let's say now I will introduce a load change. Now my load resistance is 10 ohm. I will introduce a load. I will change my load resistance to 15 ohm so that the load power will be decreased. So if I press 15 ohm and press enter button in my load box, so around 30 seconds in the recorder option, we have introduced a load change. The power required by the load is now 150 watt. The power supplied by the PV is 167 watt, and battery is absorbing the power. Now let's say I will introduce a change in irradiation. I will increase the irradiation to 750 watt per meter square. At around 61 seconds, I have introduced an irradiation change, increase in irradiation. You can observe that the power supplied by the PV panel is around 250 watt, while the load requirement is same 150 watt. The battery is absorbing the excess power of around 87 watt. Rest 10 watt is actually the loss associated with the converters. So after your experimentation is done, suppose you don't want to record more data, so you can stop the recording button. Now I have stopped the recording button, so the data is stored in the root directory in .mat file. Now what I will do, I will disconnect my battery. If I disconnect my battery, I have disconnected both your battery and supercapacitor, and you can see the DC bus is not maintained at 48 volt. It is at around 60 volt. And let's say if I reduce the irradiation to 500 watt per meter square, it is around 49 volt, and the corresponding maximum power is tracked by the MPPT controller. So now I will turn off the PV system. As I turn off the PV system, so everything comes to zero value except the value of the supercapacitor and battery. That will be directly shown. The sensors are actually directly connected across the battery and supercapacitor terminals. That's why the value of this battery and supercapacitor is shown in this display. Now you can press go offline, and your online calibration is over, and you can go into the platform or devices. Here you can see it is a green button is coming, green play button is coming. And in this, if you right click, you can stop RTP. You can press, if you press stop RTP, it will turn into a red icon. So already we have stored the data. Now I will show you how we can plot this one. So we have stored the data in our root directory. So I will go there. You can see that our file name was exp1_004. The data is stored in .NET file. You can simply drag it and you can bring it to the MATLAB command window. And you can plot the curves. You can see, we'll copy this one. I want to plot this curves. You can see that we have plotted, we have got 4 curves. Let's I will make it to 90. This so you can see that this is our PV curve, and this violet curve is our load curve. This blue line is our battery power, and this yellow line is our supercapacitor power. We can observe that here we can see that the load requirement is around 150 watt, and PV power is in excess, and that's why the battery is absorbing the excess power. And during when here I have introduced a change in load, you can see that here you can see that the battery current is smooth as the supercapacitor is absorbing the transient. The battery current becomes smooth as the supercapacitor is absorbing the transient. That's all for the demonstration. Now we will move to the again we will move to the presentation side. Now I will discuss about the calibration of sensors and various signal conditioning units are present that are associated with this setup. So this is an LEM LA55 P current sensor. This can measure maximum current of 50 ampere. So it is a Hall effect type sensor. So suppose we want to scale down a current of 10 ampere to 5 volt. So how many number of turns we have to use? See, the rating is 50 ampere, and the maximum current, whatever you want to use, whatever maximum current what you want to measure is IS max. Okay, I will quickly show you this thing. So for this case, you have to, for an input current of 10 ampere, you have to determine a burden resistor to acquire the or feed the actual current into the controller. So in this case, in our system, we have used a 100 ohm burden resistor for the current sensor. And there are certain important points that should be actually taken care while designing the current sensor. The output resistor, that is should not, if you go through the data sheet, in that data sheet it will be mentioned that it is within the range of 50 to 160 ohm. So one important thing that you should take into account is that you should not go beyond 150 ohm actually, in order to avoid the linearity and non-linearity in the measurement reading. And if you are selecting a low tolerance value of burden resistor, that will will give you a good result actually. And in order to increase the accuracy in measurement, you can use the half watt or 1 watt power resistor, power rating resistor should be selected, and you should not go for actually quarter watt resistor. Similarly, for voltage sensors, also, if you want to, suppose you want to scale down the 200 volt to 5 volt, accordingly, you have to select a 200 ohm burden resistor. In this case also, if you go through the data sheet of this LV25P current sensor, voltage sensor, you can see that range will be, the burden resistor range will be from 100 ohm to 350 ohm. So in my opinion, the output resistor in this case should not be selected beyond actually 300 ohm to avoid any nonlinearity in the measurement reading. Again, it will be good if you select a low tolerance value. Again, the thing is that if you want to increase the accuracy in your measurement, then you have to use the quarter watt, half watt or 1 watt burden resistor can be used. This one is basically the optocoupler based IGBT gate drive circuit. So it is already, this is very popular choice for gate driving applications because it provides isolation between the input side. This is basically the control side. This is basically the plant side ground. So basically this is providing the isolation in between this ground. It basically comes with a 8 LED dual in package, and the input signal or pulse that is coming from the controller is will be in the range of 5 volt actually. So it will be scaled up to 15 volt as required by our switches. So the input pulse from the, you can see the input pulse from the D space is around, it is around peak to peak value is around 3.44 volt, and the frequency is 20 kilohertz, and the amplified signal or the output of the TLP 350 is around 15.8 volt with the same switching frequency. And I think already all of you know about this dead-time circuit. Basically, this dead-time circuit is used to prevent shoot-through faults in a single leg converter. Okay. So you can see that in this blanking circuit is introducing a delay in between two pulses of around 4 microseconds. And similarly, you can follow this circuit diagram if you want to design the plus 15 minus 15 power supply or dual power supply for your sensors. Now I'm going to discuss about the experimental results that I have acquired actually. So here we are discussing the MPPT results. The experiment was actually carried out for two different irradiations, 400 watt per meter square and 300 watt per meter square. Initially, you can observe that the system is operating at 400 watt per meter square, and the corresponding power output is 115 watt. Around 54 seconds, what we have done is we have decreased the irradiation to 300 watt per meter square. So this basically causes a reduction in PV power to 87 watt. And again, irradiation is increased abruptly to 400 watt per meter square at a time of 100 seconds. So it can be seen that the PV voltage initially reduces and again tracks back the maximum value once the duty cycle stabilizes at the new value. Similarly, due to irradiation increase, the PV voltage swells up and retraces back the MPP voltage. as soon as the duty cycle is getting settled at the new operating point. This is the actually the real-time tracking of maximum power in the solar emulator. Here you can see we are getting the maximum power at an irradiation of 400 watt per meter square, and the right hand side figure represents the experimental results that are basically given by the solar array simulator computer interface that we have taken a screenshot for showing all of you actually. Now I will discuss about the experimental results that we have obtained when we have an integrated system which consists of a PV system and a hybrid energy storage system. So the experimental results are carried out for the irradiation change and load change, and the system is actually tested for normal operating SOC range of the battery and supercapacitor. For this case, I have selected 50% as my lower SOC level and 90% for the higher SOC level. And you can observe that till 14.74 second, you can see that we are getting the power output of 115 watt, and the load power is around is 105 watt. Here you can see we have not introduced, we have introduced the battery, but the battery is in floating condition. The battery power is nearby around 0 watt, and the 10 watt is the loss associated with the converter. And from time 14.74 second to 35 second, what we have done is we have introduced a load change, and the load power is almost doubled. And you can see that battery is supplying the deficit power that is required by the load, and the loss in this case is also around 10 watt. Similarly, these kind of observations are carried out, and you can see that and during your time 60 second to 84 second, what we have done is we have increased the irradiation to 500 watt per meter square, and from the previous case, actually we have reduced the load, so PV power is in excess with respect to the load, and so therefore the battery is absorbing a power of minus 30 watt actually. So you can see that in figure 3, here in figure 3, you can see that the DC bus voltage is maintained at 48 volt irrespective of change in load as well as irrespective of change in irradiation condition. So now I will conclude my tutorial session. So what till today what we have done is we have discussed the detailed design, development and control of a PV fed LVDC microgrid with hybrid energy storage system. We have done the comprehensive design details of all the elements, various elements, that is your current transducer, voltage transducer, signal conditioning unit, blanking circuits, and power supply circuits were presented. And the implementation challenges of an integrated hardware setup for each unit of the LVDC microgrid that relies on a digital controller are described. Along with that, the development of the power management scheme deployed using your our DSpace digital platform, confirming the effective mode transition are under various environmental and load disturbances were presented. And this developed 48 volt LVDC microgrid can be a promising solution for powering consumer electronics in various homes and office spaces or different small scale applications. But the thing is that you need to carefully evaluate the specific needs and requirements of the loads that you want to cater actually. So finally, this work actually presents a self-directed learning approach for students, researchers to develop a LVDC microgrid, accounting the dynamic nature of any renewable energy system, right? Leveraging on the capabilities of hybrid energy storage system within a lab. Within a lab, we can do by following all these steps, whatever we have discussed today. So for further reading, you can follow these references, particularly whatever we have discussed today. You can follow the reference number 3. In this paper, all the design details are actually presented. That the title of the paper is Design and Real-Time Implementation of Wind Photovoltaic Driven Low Voltage Direct Current Microgrid Integrated with Hybrid Energy Storage System. It is published in Journal of Power Sources in Elsevier actually. Thank you all. So if you have any questions, you can please ask.
If anyone has any questions, please ask. Thank you, Professor Monalisa Pattnaik and Mr. Pradyumna Kumar Behera for such informative session. And I hope our participants may learn about this D-space and microgrid interfacing. So now moving on towards our next speaker, Professor Susovon Samanta, NIT Rourkela. Let me introduce Professor Samanta. Professor Samanta received the ME degree from Jadavpur University, Kolkata, India in 2003 and the PhD degree from Indian Institute of...
Ananya,
Yes, ma'am.
just wait, let sir to come and we can start.
Ma'am, I think sir has already joined.
Sir will come to the upstairs. He is there in the upstairs, 401.
No. I think sir has joined online.
Sir will join there only in that room. Sir will explain on the board.
Okay.
Just wait,
Okay.
sir to be there,
Okay.
and then you can.
Okay, ma'am. So I request participants to just wait for 5 minutes. Let Professor Samant join.